Welcome back to the deep dive. If you joined us previously, you know we were meticulously analyzing the user-facing side of this application. The beautiful cross-platform interface built on Flutter. We saw the polish, the responsiveness, all that platform adaptation. But today we're doing what every engineer kind of dreams of. We're leaving the pretty facade behind, crossing the wire, and heading straight into the back end, the highly resilient, highly opinionated, clustered Node.js backend. This is the nervous system, isn't it? The brain of the operation, where all those real-time connections are managed, files get routed, and crucial decisions about economics and intelligence are executed.
Yeah, absolutely. It's the engine room, really. When you design an application that's centered around, high throughput, real-time data flow, especially file sharing, well, the backend just cannot afford downtime or latency spikes. It's just not an option. Our foundational mandate for architecting this system was kind of a tripartite commitment. Unwavering speed for I/O operations, that was number one. Then rock solid availability achieved through, fault tolerance. And finally, absolute cost effectiveness. That was crucial to make the generous user offering sustainable. Every line of code, every architectural choice we made, it was all driven by those three competing but essential goals.
And that really sets the stage, doesn't it? That's the map for our deep dive today. We're start at the foundational choice, Node.js and Express, and how they overcome that single-threaded limitation through machine-level clustering. It's fascinating stuff. Then we'll pivot to strategy, this dual cloud approach, leveraging GCP for centralized intelligence and Backblaze B2 for significant cost control. We'll finish by dissecting the custom engineering, the self-reliance needed for those in-house dynamic links, and the logistical elegance of the build distribution pipeline, before diving right into the core routes and the underlying MongoDB data model. It really is a journey into orchestration. So let's start with a why. Why this technology stack? Okay, so the core foundation is Node.js running the Express.js framework, all in JavaScript. Now, the convenience of using one language across the stack, that's a nice bonus, sure, but the architectural reasoning must be much deeper than just consistency, right? Especially for something demanding high concurrency like real-time file transfer. So why Node.js? What made it the uncompromising choice here?
It really comes down entirely to its inherent design. It's just perfectly suited for input-output heavy workloads. I'm talking about the non-blocking, event-driven architecture. If you contrast this with, say, traditional server models, they often use thread per request models. Now, if a thread is dedicated to waiting for a large file to be read from disk or waiting for a network response from a client, that thread is essentially idle, but it's occupied. And that just wastes resources, right? It limits concurrency.
Right, and Node.js just flips that script entirely.
It does. Node operates on a single event loop. So when a request comes in, say, initiating a file upload, the Node.js process offloads the actual file reading or network waiting part. It hands it off to the operating system's kernel, registers a callback function, and then immediately moves on to process the next incoming request. It doesn't wait, it delegates. That's the key. When the I/O operation finally completes, the kernel signals the event loop, and only then is the callback executed. This architectural feature makes Node exceptionally performant for the kind of simultaneous, high-volume, low-latency I/O operations needed by, a real-time file sharing and signaling service like this. It means it can handle thousands of simultaneous connections with minimal overhead, directly fulfilling that speed mandate we talked about.
Okay, that makes the I/O side really clear. But here's the massive asterisk on Node.js, isn't it? Its inherent single-threaded nature. If that single event loop hits a computationally intensive task, anything that locks the CPU, like heavy data processing, complex encryption, or maybe even that AI summary we'll get into later, it can stall the entire process, queuing up hundreds or thousands of pending I/O requests. That's the classic single point of failure, isn't it? It has to be engineered around.
Oh, absolutely. It's a known vulnerability, a known characteristic, and acknowledging it immediately led us to the solution. Horizontal scaling through clustering. We realized pretty quickly we couldn't rely solely on the intrinsic strength of Node. We had to compensate for its limitations at the infrastructure level. The goal was internal, local load balancing, and fault tolerance. And the tool for that was the Node.js built-in cluster module.
Right. So for the listener who might be familiar with Node, but maybe hasn't had to wrestle with high availability deployment, let's detail this process a bit. How does implementing clustering actually transform a single process application into, a multi-core beast? And how does the cluster module facilitate that, specifically on, say, a typical cloud instance?
Okay, yeah. The mechanism is pretty robust and actually surprisingly transparent to the application logic itself. The first process that runs is what we call the master process. Now, this master process is not responsible for handling incoming client requests directly. Its sole critical job is supervision, management. It uses the cluster.fork method to spawn multiple instances of the main Express server. These are the worker processes.
And is there a rule of thumb for how many workers to spawn? Like, how do you decide?
Yeah, we aim for maximal CPU utilization. Generally, it's one worker process for every logical CPU core available on the host machine. So if we provision, let's say, a 16-core cloud VM, the master process will immediately spawn 16 worker processes, each one running the identical application logic, each with its own separate event loop.
Okay, so now you've got the master and 16 workers. Incoming traffic hits the master process first, right? How does that traffic actually get distributed to those 16 isolated workers on the same machine?
Good question. The operating system actually handles the initial incoming connections. The master process binds to the main port, let's say, port 3000. When a new connection arrives, the kernel typically uses a technique like round-robin scheduling, basically, to hand off that connection socket to one of the available worker processes. And critically, once a worker accepts that connection, it owns it entirely. This gives you instant local load balancing that distributes the load pretty evenly across all the available CPU resources, which means, the application throughput is now multiplied by the number of cores we have provisioned.
That dramatically improves throughput, allowing heavy compute tasks maybe on one worker without stalling the whole app. But let's pause on a tricky point this scaling introduces: shared state management. If a client initiates something, or if we rely on WebSocket connections for signaling, which we know we do for real-time file transfer, how do you make sure that if a subsequent request from that same client lands on a different worker, the application still knows the client's current state or session?
Ah, yes. That is the Achilles heel of horizontal scaling, isn't it? And it's precisely why we had to ensure the application was designed to be fundamentally stateless at the worker level. A clustered architecture like this absolutely cannot rely on in-memory state storage within the worker process themselves. It just doesn't work reliably.
Okay, so where does the state live then, if not in the worker memory?
All critical application state session data, user authentication tokens, and most importantly, that complex mapping of active WebSocket connections and client registry information, it all has to live externally. We rely heavily on MongoDB for persistent state, like the client registry. And if we needed, say, caching or true session management beyond tokens, we would utilize an external centralized data store, something like Redis or Memcached. The workers must be designed to fetch any necessary state information from these external stores on basically every request. This ensures that it doesn't matter which of the 16 workers services the client, they all have access to the single source of truth.
That makes perfect sense. Decoupling state from the workers is absolutely essential for stability. Okay, now let's circle back to the second half of the mandate, fault tolerance. You said this clustering is non-negotiable for production-grade applications. How exactly does this architecture handle a worker crash? Let's say one just falls over.
This is the critical availability benefit. Because the workers are entirely isolated processes, if, say, worker #5 encounters some catastrophic failure, maybe an unhandled exception or a memory leak runs wild, it crashes independently. The master process, which is constantly monitoring its children via an internal communication channel, it immediately detects the loss of worker #5.
And the system doesn't even blink for the other 15 workers still running.
It doesn't blink. The master instantaneously registers the failure and executes the recovery mechanism. It just forks a brand new worker process to immediately replace the failed one. This new worker quickly spins up, initializes, and joins the pool, ready to accept incoming connections. Crucially, the users whose requests were being handled by workers #1 through #4 and #6 through #16, they experience zero service disruption. So the availability mandate is met by engineering redundancy right into the core runtime environment itself.
That explains the massive leap in stability. Okay, before we move on from node and clustering, I have to ask the critical engineering debate question here. Given the complexity of managing state externally and running multiple processes, why didn't the team maybe favor a language like Go or Rust? Something that could handle highly concurrent CPU-bound tasks natively within a single process, potentially simplifying the deployment model.
That's a fantastic question, actually. And it really speaks to the ultimate trade-off, doesn't it? Development speed versus raw performance complexity. Look, while Go or Rust offer phenomenal concurrent performance natively, no question, they also introduce significant cognitive overhead, development time, library maturity, ecosystem. And in this specific case, language integration was a factor too. Node.js lets us leverage the massive ecosystem of JavaScript, which sped up development immensely, especially, integrating with the front-end team who were already on JavaScript via Flutter Dart. We basically accepted the necessity of clustering as a structural fix to Node's single-threaded nature. We judged that the performance gains from non-blocking I/O, coupled with the stability of the clustering module, well, they outweighed the cost of potentially slower development in another language and the complexity of managing those external state stores required by a different language stack. We decided to solve the CPU problem through infrastructure orchestration using clustering rather than through a more complex foundational language choice.
A very clear, performance-driven trade-off. Okay, so we've solved speed and availability locally through this elegant clustering solution. Now let's connect this to the broader cloud architecture, focusing on economics and intelligence. Right, the architecture seems defined by maybe avoiding vendor lock-in and picking the right tool for the specific job. This resulted in this fascinating dual cloud strategy. Let's start with the use of Google Cloud Platform, GCP. This seems to be where the application finds its intelligence and ensures its own continued health.
Yeah, GCP is kind of our operational brain in many ways. While the Node.js instances are incredibly fast, they are decentralized clusters, right? 16 workers, potentially across multiple machines. We need a single point of truth for monitoring everything, and we need a specialized environment for the heavy computation stuff.
Okay, let's talk about server health monitoring first. How do you actually manage logs and metrics from potentially, 16 different worker processes, maybe even spread across multiple machines? That sounds like a nightmare.
Yeah, it would be impossible manually. We centralize absolutely everything using GCP logging. It's just not feasible to debug production issues by SSHing into a machine and trying to tail individual logs from 16 different workers simultaneously. Forget about it. Instead, every critical event, every auth attempt, every file transfer initiation, every unexpected crash, every API request latency metric, it's all streamed out of the Node.js processes and piped into a single unified GCP logging destination.
And what does that centralization allow you to do proactively? How does it help before things break?
It lets us manage health proactively through sophisticated log analysis. We can immediately set up filters and alerts on specific log patterns. For example, we might define an alert that triggers if the combined error rate across all workers for, say, API requests exceeds 3% within a rolling 10-minute window. That tells us something's wrong now. We can also track memory usage trends for specific workers over time. If we see worker #12 consistently spiking in heap usage, that points us immediately to a potential memory leak in a specific code path. That allows us to maybe restart just that worker or deploy a patch before it seriously affects service quality for users. It transforms firefighting into, anticipatory maintenance.
That's managing the system's health. Now, for the intelligence side, the AI file summarization feature. This sounds like a major value proposition for the user. Generating text summaries or metadata from uploaded documents. We established earlier this is a CPU-bound task, something that absolutely cannot run on Node's single event loop without causing chaos. This led to what you call the orchestration twist, running a dedicated Python service alongside the Node cluster. Can you elaborate on that?
Yes, exactly. This is where we prioritize specialized execution. Python is, let's face it, the industry standard for machine learning, so that we use it to run the processing model. Specifically, we leverage the Gemma model. That's Google's lightweight open model family of large language models. It was chosen specifically for its balance of performance and relatively low resource requirements for the kind of summarization tasks we needed.
But the key question is the integration, isn't it? How does the Node.js orchestrator reliably hand off these tasks to this Python microservice and then get the results back, all without burdening the main external API?
Right. We engineered the communication using a lightweight REST API running on the local loopback interface, localhost. This is absolutely crucial. When Node.js detects a file upload that requires summarization, it simply sends an HTTP POST request internally to something like http:127.0.1.8080 summarize. That's whatever internal port the Python service is listening on. The request contains the file path or metadata needed for the job.
Why specifically the local loopback interface? Why not expose it more broadly?
Speed and security. Because it virtually eliminates network latency. The communication literally never leaves the host machine's memory stack. Doesn't hit the network card. It's the fastest form of inter-process communication, IPC, available short of using maybe Unix domain sockets, which are often more complex to manage, especially between different runtimes like Node and Python. Node.js acts as the traffic cop here. It verifies the external request, handles the secure file upload to B2 first, and then asynchronously delegates the analysis request to the Python service. So the node worker process is only briefly busy forming and sending that internal HTTP request. It then immediately continues handling other external API calls while the Python service chews through the ML processing in the background.
So the result is that the user gets confirmation their file is uploaded almost instantly because the main API remains fast and responsive. And the intelligent summarization just proceeds reliably in the background via that specialized Python service. It's quite elegant orchestration.
Precisely. It's about using the right language Python for the right computational task ML processing without sacrificing the core performance of the Node.js layer, which is absolutely essential for I/O and signaling.
Okay, now let's transition from intelligence to pure economics storage. The choice here was Backblaze B2. That means moving away from the storage services usually offered by the big three cloud providers. What was the driving strategic motivation behind choosing B2 specifically for object storage?
It was entirely driven by the third pillar of our mandate, cost effectiveness. Simple as that. When your business model is based on providing generous amounts of storage, the unit cost of that storage becomes the defining factor in your long-term sustainability. It's make or break. Our extensive research showed B2 offered a significant, measurable cost advantage. The sources confirmed it was consistently somewhere between 18% to 21% less expensive than comparable services from AWS S3, Azure Blob Storage, or GCP Cloud Storage. And that's especially true when you factor in data retrieval costs, egress fees, and transaction costs, which can really add up.
Wow, that 18% to 21% cost saving, scaled across potentially millions of users and terabytes or even petabytes of data. That is massive. How does that translate directly to the listener to you using the app?
It translates directly into the generous 15 gigabyte free cloud storage baseline we can offer every single user. To put that in perspective, if we had gone with one of the traditional big providers, that 18-21% higher cost would either force us to drastically reduce the free tier, maybe down to 5 gigabyte, maybe even less, or it would dramatically inflate our operational expenses, which could possibly jeopardize the entire financial model of the service. Choosing B2 allows us to maintain a really generous offering, fulfilling our value proposition to you, the user, while keeping our own costs manageable.
That's a powerful engineering decision wrapped up in an equally powerful business decision. But okay, every cost saving usually has a potential trade-off somewhere. When integrating a storage solution that isn't one of the big three, what challenges did the team face? Did B2's API maturity or integration complexity introduce any new engineering hurdles compared to, say, just pulling in the well-documented AWS SDK?
That's a really crucial point. Yes, there was a trade-off. While B2 is mature and reliable, integrating it required slightly more hands-on effort, definitely. Their SDK and documentation, while good, didn't always have the immediate massive community support or perhaps the same breadth of pre-built features that something like AWS S3 provides right out of the box. Years of community examples and libraries. So we had to dedicate more engineering time to handling some custom API logic, particularly around managing file lifecycles correctly and ensuring really robust upload verification and security protocols were in place. There was definitely a trade-off in initial engineering complexity, yes, but that ongoing 18-21% saving vastly justified that upfront investment. It pays dividends constantly.
Makes sense. Okay, so once a file is successfully uploaded to B2, we need to make it shareable. You mentioned the custom UX enhancement of unique links and also QR codes. How does the backend leverage that B2 file to create a shareable, simple experience for the user?
Our Node.js API acts as the gatekeeper for all shares. Once the file is safely stored in B2, the API generates a unique, cryptographically secure internal token. This token is linked directly to that specific B2 object. The shareable link presented to the user actually contains this unique token, not a direct B2 link. When another user or recipient clicks that link, the request hits our Node.js server first, always. The server validates the token, checks access permissions like, is the file meant to be public, is the user logged in and authorized, and only then does it either serve the file directly from B2, acting as a proxy, or more likely provide a secure, time-limited redirect URL directly to the B2 object.
And the QR code feature, how does that fit in?
The QR code is simply a visual representation of that unique, controlled, shareable link we just talked about. The sharefileroute.js, which we'll look at in more detail later, runs the logic to instantly render the QR code graphic based on the link and sends that image back to the client application. This is a massive UX improvement, honestly, especially in cross-device sharing scenarios. Think about sharing from your phone to someone else's phone right next to you. You completely eliminate the need to copy, paste, or email links. You just hold up your phone, they scan the code, and boom, they have the file or the download starts. Frictionless exchange, that was the goal.
Seamlessness and control seem to be defining themes in this architecture. We move now to some really interesting custom features, starting with dynamic linking. Now, for anyone who's managed mobile applications, you know dynamic links are absolutely essential for opening the right content within the app at the right time. The impending shutdown of Firebase dynamic links caused, well, a huge systemic risk for many developers relying on it. You chose to build this functionality entirely in-house. What specific risk were you trying to mitigate by opting for that kind of self-reliance?
Yeah, we were primarily mitigating the risk of future platform deprecation and, frankly, unexpected service changes from third parties. It happens all the time. Relying on a third-party service for fundamental routing logic like this means you're effectively giving up control over the user's primary journey into your app from a link. We absolutely needed dynamic linking to work perfectly, especially for shared files. If I click a link someone sends me, it must open the specific file page within the native app if I have it installed. Or, if I don't have it, it needs to direct me to the correct app store to get it. That flow has to be seamless. Betting it in-house meant we gained total control, guaranteed reliability, and ensured longevity, completely irrespective of, say, Google's product roadmap decisions for Firebase or any other service.
Okay, so this is implemented as a server-side redirect mechanism, living within specific express routes in the Node.js backend. Can you walk us through the exact server-side logic? What's the dance between the client clicking the link and the server figuring out where to send them?
Sure. The process kicks off the moment the HTTP request hits the Node.js server via that custom share link URL. Step 1, and this is the magic piece of data, really, the server immediately inspects the user agent header of the incoming request. Remember, the user agent is that string sent by the client's browser or the mobile app's web view that identifies the operating system, iOS, Android, Windows, the device model sometimes, and the browser version.
Got it. So the server is essentially running an immediate platform identification test based on that header.
Exactly. The server uses some pretty complex regex matching and string analysis on that user agent string to determine the requesting platform with high accuracy. Is it running Safari on an iPhone? Is it a Chrome web view inside an Android app? Is it Firefox on a desktop? This determination is everything for the next step. Okay, so once the platform is identified, the Node.js server executes a calculated HTTP redirect, usually a 302 found, or maybe a 301 move permanently. If it identifies Android, for instance, the server issues a redirect to the application's custom Android deep link scheme, something like myapp.file file token. If the Android OS detects that scheme and the app is installed, the app opens instantly right to the correct content using that token. If the OS doesn't recognize the scheme, meaning the app isn't installed, the server then executes a fallback redirect, sending the user to the Google Play Store page for the app.
And for Apple devices, iOS uses a slightly different mechanism, doesn't it? Universal links.
Correct. For iOS, the server uses universal links. This requires some specific server configurations, like hosting a special file called the Apple App Site Association file at the root of the domain, though the redirection logic itself is quite similar. The server redirects to the universal link URL associated with the content. iOS itself then handles routing that request directly to the installed app, bypassing Safari if the app is present. If the app is not installed, or if the user agent indicates a desktop platform, Windows, Mac, Linux, the server executes a final fallback redirect. This usually goes to a generic web-based landing page. That page provides alternative download links, App Store, Play Store, desktop installers, and maybe even web access options. This multi-layered redirection logic ensures that every single click results in the most desirable, most seamless outcome for whatever platform the user is on. It guarantees we control that entire user journey from link click to content view.
That level of custom control really does guarantee reliability, which is paramount when you're talking about sharing files between users. Okay, the second major custom feature you mentioned addresses an internal logistical bottleneck. That's the distribution of cross-platform builds. Android APKs, Windows EXEs, Linux builds, iOS builds, distributing those to internal testers and early users without relying on expensive, often complex, commercial distribution platforms like TestFlight or App Center.
Yeah, exactly. Managing beta testing or internal insider rings across potentially 4 different platforms, iOS, Android, Windows, and Linux, can quickly become a huge time sink, almost a full-time job in itself. So we implemented a custom build distribution pipeline. It's intrinsically linked to our CI/CD process, our continuous integration and continuous deployment system. The goal was super simple: low friction, high-speed delivery of internal updates to our testers.
How does the CI/CD pipeline actually interact with the Node.js backend to make this happen? Where does the build go?
Okay, so once the CI/CD system successfully compiles and verifies the latest build artifact let's say it's the new Windows executable, instead of just storing it away in some internal artifact repository somewhere, the CI/CD agent makes a secure, authenticated API request to a dedicated endpoint on our Node.js backend. It pushes the artifact itself, the exe file, the APK file, etc., and its metadata, things like the version number, build date, maybe even a short changelog. Our Node.js server then takes this artifact. It probably stores the actual binary file back on B2 for cost efficiency, but manages it securely, and it updates a central manifest file, likely stored in MongoDB. Testers then access a single unified web page. That web page simply queries this manifest via a specific route on the backend. The server reads the platform of the incoming tester's device, again, using that trusty user agent, presents the download link for the latest appropriate build, for example, the latest Android APK for someone visiting from an Android phone, and serves the secure download link, probably pointing back to B2.
Okay, so it completely centralizes distribution and eliminates all that manual overhead of updating download links on different pages or managing multiple platform-specific portals.
Exactly. And it's super cost-effective because we avoid all those third-party platform fees, which can get quite expensive. Plus, it keeps the feedback loop exceptionally tight. An engineer can push a code change, CI/CD runs its magic, and maybe 15-20 minutes later, the very latest build is available to the entire internal test group via a single persistent URL they already know. It's really engineering logistics designed specifically for rapid iteration and testing.
Okay, we've examined the high-level strategy, the cloud choices, and those Flutter custom features. Now let's get down to the brass tacks of the code base itself. If we were to peek inside the application server, what does the organization under the main C folder tell us about the engineering philosophy behind it all?
Yeah. The organization under SarinRC really reflects a strict adherence to the principle of separation of concerns. This is absolutely critical for the long-term maintainability of any system, but especially one designed to handle both real-time and asynchronous tasks like this one. We're aiming for maximal clarity, really, ensuring that any engineer, whether they're new to the project or experienced, can immediately locate the domain logic, the configuration settings, or the data access layer without having to hunt around.
Makes sense. Can you walk us through the critical folders then, maybe starting with configuration?
Sure. We begin with config. Pretty straightforward. This folder holds all the environment-dependent variables and static configurations. This includes stuff like database connection strings for Mongo, the port the cluster binds to, the API secrets for interacting with Backblaze B2, and the keys for the Razorpay payment gateway integration. Centralizing all configuration like this ensures secure deployment practices. Crucially, we don't hard-code secrets directly in the code, and it massively simplifies shifting between different environments, like development, staging, and production. You just change the environment variables.
Okay, next, the real engine room, controllers and middleware. What's the strict division of labor between these two? They often get mixed up.
Yeah, we try to keep a very clear line. Controllers are purely responsible for the business logic. A controller takes the inputs, which have already been validated by the middleware, decides what external services, like B2 or the Python service or data models need to be called, orchestrates the flow of data between them, and finally formats the response that gets sent back to the client. Controllers essentially answer the question, what is this specific API endpoint supposed to do? Middleware, on the other hand, answers the question, what must happen before or sometimes after the main API logic runs? Middleware handles those cross-cutting concerns that apply across multiple different routes. The most common examples are things like authentication, checking JWT tokens, verifying user sessions. Also, data validation, ensuring incoming request payloads are correctly structured before they even hit the controller, logging every request, maybe rate limiting to prevent abuse. By handling these common concerns in dedicated middleware functions, our controllers remain lean, clean, and focus entirely on the core file sharing logic, making them much easier to read and test.
Got it. And then we have the data and service layers. Model, services, and utils.
Right. Model is where we define our MongoDB data schemas using Mongoose. Mongoose helps enforce some structure and apply validation rules even within a NoSQL database like Mongo, which is really helpful. Services is critical. This is where all the logic for interacting with external systems lives. So the code for connecting to the B2 API, the logic for communicating with that internal Python summarization service over localhost, and any complex payment processing logic involving Razorpay, it all resides here. This abstraction makes it much easier to swap out or update these external dependencies later without having to touch the core controller code. You just update the service implementation. And utils is basically the miscellaneous helper function library, things like date manipulation functions, token signing utilities, or specialized data formatting functions that might be used across various parts of the application, general reusable bits.
Okay, finally, routes. The entry point for everything coming into the API. This is where the application's functional identity is really defined, isn't it? Let's break down the purpose of the most crucial routes, maybe starting with identity and that real-time signaling piece.
Absolutely. So user route.js handles pretty standard identity management. User registration, login, issuing JWTs, perhaps profile updates. This is your standard secure authentication flow. But as you highlighted, the real complexity for the real-time aspect begins with client-register-route.js. This route is absolutely foundational. It's the cornerstone for enabling local peer-to-peer file sharing and presence detection.
You call this route crucial. We probably need to go a bit deeper into its function. What exactly is happening when a client, an app on my phone or desktop, registers its IP and port, and why is that information so vital?
Okay. When the mobile or desktop client application starts up and successfully authenticates with the user route, one of the next things it does is send a request to this client register route. In that request, it registers its current local network details, specifically its internal IP address like 192.168.1.100, and a specific port number it has opened locally for potential peer-to-peer communication. The server takes this IP port pair and maps it directly to the user's unique global ID, the one used for login, storing this mapping in a dedicated MongoDB collection in the client registry. Now, this registry effectively acts as the central signaling directory or phone book for local connections. When user A wants to send a file locally to user B, who might be on the same Wi-Fi network, user A's device asks our server via another route, "Where is user B right now on the local network?" End quote. The server queries this registry, finds user B's currently registered local IP and port, if they're online and registered, and sends that information back to user A. User A's device can then attempt to establish a direct peer-to-peer connection to user B using that IP and port. This is the signaling layer that happens before any file data actually moves. The server is acting purely as a broker, a matchmaker here.
Okay. And that brokering process, the attempt to connect, and then the fallback, is managed by filetransferroute.js.
Correct. This route manages that dynamic real-time signaling for the local transfer attempt. It often utilizes WebSockets for near instantaneous communication between the two clients, but still brokered through the server. Crucially, if that direct peer-to-peer connection attempt fails, which happens surprisingly often due to complexities like NAT traversal, different subnets, or just strict firewalls, this route seamlessly executes the fallback logic. It switches the transfer mechanism automatically to an upload-download cycle via the Backblaze B2 cloud storage. User A uploads to B2, user B gets notified and downloads from B2. This route ensures that the file transfer always completes one way or another. It prioritizes speed, local PDP first, but absolutely guarantees reliability. Cloud fallback.
Makes sense. Okay, moving to the pure storage interface side, we have Backblaze root.js and cloud storage usage root.js.
Right. Backblaze root.js is essentially the core translator between our Express API logic and the actual Backblaze B2 API. It handles all the low-level object storage operations, generating upload URLs, handling download requests, managing secure temporary token exchange with B2, and ensuring data integrity during uploads and downloads using checksums, etc. Cloud storage usage root.js is also essential, particularly for billing and user accountability. It's responsible for querying the stored file metadata, which we keep in MongoDB, and potentially even querying B2 directly sometimes to calculate a user's real-time cloud storage consumption against that 15 gigabit free baseline. Accuracy here is absolutely critical, both for potentially charging for premium tiers and just for maintaining user trust by showing them exactly how much space they're using.
And tying back those custom UX features we discussed earlier, we have ShareFile or root.js.
Yes, this route is the nexus of all our sharing logic. It centralizes the generation of those unique, secure file sharing tokens we talked about. It coordinates the QR code rendering process, calling the utility to generate the image. And crucially, it contains the core logic for that in-house dynamic linking mechanism. It processes the incoming request's user agent header and determines the appropriate platform redirect to the App Store, the deep link, or the web fallback, ensuring that seamless journey when someone clicks a shared link.
Okay, and finally, ensuring the whole thing can actually sustain itself financially, we have the monetization route, payments route.js.
Yeah. This route manages the entire upgrade lifecycle for users wanting to purchase premium storage beyond the free tier. We chose Razorpay as the payment gateway, largely for its robustness and strong support for localized payment methods, particularly in certain key markets. This route handles the secure initiation of payment sessions with Razorpay, listens for incoming webhooks from Razorpay confirming successful or failed transactions, and, upon success, updates the user's storage quota directly in their profile within the MongoDB model. This has to be a highly secure and extremely reliable route, obviously, as it represents the critical revenue stream that sustains the entire operation, allowing us to keep the base local services free and the cloud storage tier generous.
We've mentioned the data store frequently throughout this. The choice was MongoDB. Given the requirement for high concurrency, real-time updates for the client registry, and the need to manage quite varied types of data user profiles, detailed file metadata, that dynamic client registry info, why was a NoSQL database like MongoDB chosen over maybe a more traditionally structured relational database like PostgreSQL?
Good question. MongoDB was chosen for essentially 3 primary reasons: performance, horizontal scalability, and schema flexibility. First, performance. MongoDB generally excels at handling the high volume of concurrent reads and writes generated by things like real-time signaling and updating that client registry constantly. Its native document model also aligns almost perfectly with how modern APIs typically exchange data, JSON, which minimizes the friction, the impedance mismatch, often found when trying to map complex JSON objects neatly into rigid relational tables.
Right. The flexibility aspect seems key, too.
Absolutely. Schema flexibility is huge for rapid iteration and dealing with diverse data. Consider file metadata. The metadata we might want to store for a higher resolution video file, things like codecs, bitrate, duration, aspect ratio, is entirely different from the metadata relevant to a PDF document page count, author, maybe that AI-generated summary text. With MongoDB, we can store these vastly different data structures within the same files collection without needing complex, potentially locking schema migrations every single time we want to introduce support for a new file type or add a new optional metadata field. This allows the engineering team to iterate on features much, much faster. And crucially, that client registry information mapping user IDs to those constantly changing local IP port pairs is perfectly suited to the document model. It involves frequent, rapid updates and very fast lookups based on the user ID. MongoDB handles this kind of churn reliably, even under the high load generated by thousands of devices constantly connecting, disconnecting, and re-registering with the clustered Node.js backend.
This has been a truly comprehensive look at these backend blueprints. Wow. If we were to try and synthesize this entire architecture down to maybe one core concept, I keep coming back to the term you used right at the beginning, orchestration.
Absolutely. I think that's the perfect word. The success of this backend is defined by its ability to act as a really brilliant traffic cop and an expert delegator. The clustered Node.js server doesn't try to be everything to everyone. It focuses intensely on its core strength, which is lightning-fast I/O, and managing that real-time state for signaling. When faced with tasks, it's not suited for heavy compute for AI summarization or long-term cost-effective bulk storage. It delegates efficiently. It routes the data flow intelligently, manages the state of those real-time transfers via its client registry, and ensures that computationally intensive side tasks get shunted off cleanly to specialized tools, like that internal Python microservice or external services like B2.
And the outcome seems to be a remarkably resilient, fast service that successfully meets all 3 of those initial mandates: speed, availability, and cost effectiveness. It's a really compelling case study in using specialized tools effectively and leveraging strategic cloud partnerships.
Yeah, I think it demonstrates a real commitment to engineering efficiency, recognizing that maximizing that 15 gigabit per T tier for you, the user, is just as important an engineering goal as minimizing API latency through clustering or clever orchestration.
This gives us a really complete view of the deployed application architecture itself. So what are we turning our attention to next time? We've seen the brain, the body, the internal logic. Now we kind of need to see how this entire complex system is brought to life, maintained, and scaled up in the real world.
Right. Our next deep dive is going to focus squarely on the operational layer, DevOps and CI/CD. We need to examine how we actually manage the deployment lifecycle of this, let's face it, complex, clustered, dual runtime architecture in production. We'll explore the migration strategy. How does a service like this potentially scale from, say, a smaller, simpler platform like Render, maybe where it was prototyped, into a secure, fully containerized, globally scalable cloud environment? We'll look at the deployment pipelines, the continuous delivery methods used, the monitoring and alerting setups in more detail, and the infrastructure choices necessary to ensure this service can reliably handle potentially millions of users worldwide with hopefully zero downtime.
That journey from proof of concept to global scalability is always fascinating, the practicalities of it. But before we wrap up today, let's just quickly revisit that key architectural trade-off we touched on earlier, the one that makes this whole system so fast in certain aspects. The decision to run that dedicated Python microservice handler internally, managed by the Node.js server, rather than spinning it up as a fully separate containerized service, maybe talking over a network.
Yeah, that speed benefit, the reduction in local latency for those summarization tasks, that's the immediate tangible reward of that specific choice. It's definitely performance optimization at its finest in that narrow sense.
But I want to leave the listener with the potential structural challenge inherent in that decision. While that internal orchestration is undeniably fast now, what long-term logistical and maybe engineering hurdles might the team face as the application grows significantly? Precisely because they're maintaining two separate runtime environments, Node and Python, so tightly bound within the same service architecture.
Yeah. The challenge really comes down to independent scaling and specialized maintenance. It's a classic coupling issue. By embedding the Python service handler internally, the engineering team has effectively tied the fate of two fundamentally different environments together. Imagine if the demand for AI summarization suddenly spikes, say. Users start uploading millions of documents constantly that need processing. The Python service needs more CPU, more memory. It needs to scale independently. However, because it's running inside the Node.js service boundary, you can't easily scale just the Python capacity without also scaling the entire clustered Node.js monolith along with it, even if the Node part isn't resource constrained. This also means you need two separate, specialized skill sets readily available for debugging and patching issues within that single deployment unit, but you can often only deploy fixes for either environment together as one package. If you are using a fully containerized architecture where the Python ML service lived in its own Docker container, completely separate, maybe communicating via message queue or a dedicated internal API gateway, you could dynamically scale the Python service instances up and down based purely on the ML workload demand, completely independent of Node's I/O needs. Maintaining that internal complexity, that tight coupling, is a constant engineering tax. It's a debt that may, over time, start to outweigh the initial latency gains achieved by keeping it local. It's the ultimate complexity versus performance balancing act that, frankly, every scaling startup has to constantly reevaluate as they grow.
A really profound thought on technical debt, coupling, and architectural choices over time. Thank you so much for guiding us through the intricate complexities of this clustered smart backend today.
My pleasure. It was great digging into it. And yeah, looking forward to diving into the DevOps side next time.
Until then, keep questioning your architectural trade-offs and keep diving deep.